So it's, do you have to draw the picture? No. But if you don't draw the picture and you make a mistake, I will take off more points. Oh, shit. So you better get everything exactly right if you don't draw the picture. Man, I mean.
If you get the right answer, but
You're fine.
the artwork is fine, then no points off for that.
Of course, yeah. And I wouldn't call anything I do artwork. So, I don't know, maybe you could do better. So that's what I want there. All right, so I already know the answer is going to be more than 50%, right? I can tell that from the way of drawing the picture. I put everything in the right place. What do you guys get when you look up 1.72? 9573. Okay. Sounds about right. So it's almost 96%, not quite 96%, below a z-score of 1.72 in a normal curve. So if your height had a z-score of 1.72, that would mean you're taller than almost 96% of others. Right? Normally I do height for men, height for women, because those are two very different populations. You guys with me? American men, American women, because like New Zealanders have a different average height, and so forth. Okay, all right. Is everybody with me? A little bit. Part B is the same thing we just did, except there's two areas. We got to subtract to get in the middle. So here's 2.34. Here's negative 0.91. Want that area. What do you get when we look up 2.34? 9904? What about when you look up negative 0.91?
1814.
That's a good year. And then what do you get when you subtract those?
809.
809? That sounds familiar. So are we cool with that? I mean, that's a very physical idea. It's awesome. And 9904 is too much. It just keeps going, and I want it to stop. So if I cut off that much, I force it to stop. Bam. Okay. Now this guy is giving me an area. The 21st percentile has to be down here, so it only has 21% below it. And the closest you can get to 0.21 when you look it up is 0.2090, which is what z-score?
Negative 0.81.
I like it. The other option is 19 away, and this option is 10 away. So this is the closer one. If you split the difference, that'll be okay, even though they're not exactly in the middle. Okay. Is everybody cool with that? Why did I not have to go further than this? Because this is a z-score problem. I don't have any mean and standard deviation. I can't change it into a raw score, into an x. I can do that down here. We're not there. Okay. So this one, what goes in the middle? So where's 60? Okay. Okay. So that part, if you have trouble with that part. But the big thing is not that people don't know that. It's just that people don't realize it's important. They just throw shit down here and go, well, now I got stuff for the picture that make Jeff happy. It's supposed to help you. Where am I going to shade? Right. So I know the answer is going to be bigger than 50%, right? You guys see what I mean? So if you get like 9%, you're wrong. You know you're wrong. You should know you're wrong. You probably forgot to do what? 1 minus to get the other side, right? What do I have to do now? Yeah, make this into a z-score so I can use that chart of answers. Then you could take this chart with you. Sorry, I'm playing too much Breath of the Wild. So what do you guys get for the z-score here? Yeah, negative 1.36. So that's a z-score. So when you look at that z-score, you're not going to get the answer. What do you get? 0.086. Yeah. And you know that's not the answer because you were very nice to yourself and you shaded where the answer was and you put the number you got below what you looked up. Just being so nice to yourself. So I know I'm not done. I need this side. Yeah, thanks everybody. All right. Is that what you got? 9131?
Yes.
All right, lock it. And this guy is going to be just like this guy was the minute I make both of these into z-scores, right? So in the middle again goes 72.4, 88, and 95 are up there somewhere, blah, blah, blah. Let me cut to the chase here a little bit. What do you guys get for a z-score for 88?
0.71.
0.71?
1.71.
1.71. What about for 95?
2.48.
2.48? Okay. Let me stop for a second, you guys with me? And then if I look those up, I never subtract z-scores because then I'm somewhere else. Z-scores tell me where I am. So when you look up 2.48, what do you get?
9934.
99.34? And 1.71?
9564.
So when you subtract those two, you get
0.037.
kick ass. Kick ass. All right. Okay. All right. What about this guy? I mean, go with your gut sometimes. This is funny. Go with your gut unless it's wrong. All right. But top 8%, where is it going to be on the chart? Up. Yeah, top 8%. It's going to be right there. Does the z-score chart understand that? No, it only understands areas that are below. So what's this?
92%.
So another way to say top 8% is what percentile?
97.
92nd percentile. Kick ass. So when you look it up, what z-score you guys get? 1.41. You could do 1.405. That would actually be kind of beautiful because it's almost exactly in the middle of 2. Do you have to? No. So then, is that the answer though? I kind of hope not. A grade that puts somebody in the top 8%. So I got to change it back into a raw score, and that's how I do it. The reverse of the z-score formula. So the mean was 72.4. Go up 1.41 steps. And where do you guys end up?
85.27.
Uh-oh, what happened? Say it again, sir.
85.
85.27.
27.
Okay, thank you. That's good hearing. All right. Let me show you something. I showed you. Let me show you this one more time. This is just to check your work. But like this problem, here's how I make the calculator do the whole problem by itself. You know, once I put shit into it. Distributions right up there. Distributions. Do you have to know everything I'm doing right now? You don't have to know this at all. If you want to tune out, you can for a little bit. They go to normal CDF, normal cumulative. I want accumulating between two things. The lower one was 88. The upper one was 95. The mean was 72.4. And let's see what it tells me. 037 basically. 037. 0371. Why is it not exactly the same? Because what do we do with our z-scores? We round it to two places. So technology is going to pick up the extra stuff that we lose by rounding. Jeff is not concerned. I like to sacrifice accuracy for understanding. Okay. So if you don't understand that, I won't. Any questions on that handout? All right, now. We've got to do chapter 7. Let me give you this here.
This is chapter 4, Steve?
This is chapter 6. Yeah. All right, this is gonna be weird. If you weren't here yesterday, I'll quickly give you this example again. Let me do this. I didn't actually go this far, I don't think, yesterday. Sure, I'll just do it up there. Do it live. Is this the ones I want to use? Yeah. Good. Hot. So now watch this. Let's say I go to, let's say multiverse theory is real. I go to a different universe. I go to a different universe, Florida, and I start asking people how old they are, right? And every time somebody tells me how old they are, I put a dot for their age. So say this is 0 up to 120, right? So say, how old are you? I'm 2 months old. Wow, you talk, this is amazing. How old are you? I'm 97. Okay, all right. I don't know why that, 97. They've been through some shit. So I plot. Now this is what we do to make any distribution we work with so far, is I talk to somebody, I get a value, and I plot it. Sometimes we make a histogram and I kind of collect values together, but it's still individual answers that I'm plotting. So let's say it ends up, so then watch, what does this mean then if it ends up looking like this? Was there anybody, like where's the average of that? Right in the middle. It's kind of symmetric to the middle, isn't it? You know, the kind of, why do they look like this? Because there's very few people that were this age. But there were a lot of people that were this age. See what I mean? So there's, people down there surfing and shit, whatever, and there's people down there playing shuffleboard, Boca Del Rey, retirement, right? Okay. That's why I like to use Florida. I used to live in Florida, did my time. So let's say this is the mean. It was right there. So this is from asking individual people how old they were and then plotting. So who's this person right here? They were 121 years old, right? And there are a few people that were 121. Do you see that? All right, and then this person was like maybe, I don't know, freaking 102 or something, right? You guys with me? So so as I plot, as I get ages that are the same, it makes the thing go higher, which we're used to. The height of it tells me the amount that we're at that value. It's pretty cool with that picture. Okay, now, instead of talking to individual people, I collect every group of, let's say, size 10. Every group of 10 people I can. So I take a group of 10 people in Florida, and I say, figure out your average age, and then they tell it to me after I double check the work, right? It's Florida. So what's going to change here? What's the most likely thing to happen? Is it very likely that all 10 people are from right there? No. Does everybody agree? That would be really weird if I randomly pick 10 people and they're all 119 years old. You with me? I like it, because I don't even know there's that many 119. But this is a different universe. What's the most likely thing to happen? Let's see if somebody can.
Everyone's in the middle.
Can I get anybody in the middle?
No, I mean like the middle of it.
Oh, okay. So the most likely thing to happen is a mixture between the two, right? What would you expect to happen? You would expect to get ages from all over if you randomly select. You guys semi with me? Does that mean that's always going to happen? Is it impossible to get 10 119-year-olds? Of course, if there's 10 of them, yeah, you can get 10 119-year-olds. Why not? So what I'm saying, what's the most common average then? If the most common thing to happen is a mixture of people, what is the most common average I would get?
Mean.
The actual mean. So for individuals, is anybody in here, this is some kind of weird ass middle of the road Logan's Run thing, right? Anybody know Logan's Run? Nobody?
Nobody here over 35.
Huh?
Nobody knows because none of them are over 35.
Oh, this is a good point. This is a good point. Somehow I escaped it all. So, Logan's Run is a movie where if you hit a certain age, was it 35?
I think so.
All right. Hit a certain age, you were killed because you were like a burden to society. So those people kind of, Logan tries to escape when he's, so it's, anyway, you should watch it. The special effects don't hold up, but okay. Ignoring that. The most likely thing to happen is a mixture. So right now, there's no individuals that are in there. But the most likely average I will get every time I take a sample is going to be this. That's what I would expect to happen. So if I told you the average age of 1,000 people over there is 30, what's your best guess for the average age of 10 people I select? 30. Will it be 30?
No.
Not necessarily. But I would expect it to be at least close to that, if not that, most often. So now watch. What's going to happen to this new picture now? This was individuals. This is one person at a time. Now I'm taking 10 people. What's going to change? The biggest peak is going to be right here. Because that's the most likely thing. And then probably it's going to have a little peak here and a little peak there to go along with these peaks. Do you see that? This is really gross, but oh, too bad. The most likely thing to happen if I take 10 people randomly is I get a mixture and they average to be in here somewhere. Now, this picture is not nice, but is this picture more normal than it was to begin with? Yes. So once I get to let's say 50, let's just jump all the way up to 50. So this is 10 at a time. Once I start taking 50 people at a time, it's going to be crazy unlikely to get in extremes. It's going to be much more likely to be in the middle. If I take 50 randomly selected people, if I happen to get some older, I should get some younger to average it out. That's if I randomly do it. So it's actually, believe it or not, it's going to end up looking like this.
Is that part of the law of large numbers you talked about?
Sort of. The law of large numbers has a lot of applications beyond just probability. But it's something called central limit theorem. So there's a couple things. In fact, I should have made this even better, but oh, too bad, too late, Joe. Well, I'm going to change it. Once you're at 50, it actually is going to be even skinnier than that. So, help me out. Which one of those three pictures has the largest standard deviation? First one. Which one has the smallest standard deviation? The last one. As you take larger and larger samples, it gets harder for a sample to be very different from the actual average. If I took 80 randomly selected people, the probability their average height is 6 foot tall is not likely. That's a little too far away from the average. If it's all dudes, they should be around 5'9". Very unlikely to be bigger than 6 foot average. Does that make sense? So the standard deviation definitely got smaller. What about the actual mean? So now watch this. Let me see if you guys get this. If I took everybody's age and averaged them, I'll get an average age. Amazing. If I took every 2 people average, 2 people average, 2 people average, and then averaged those averages, would it be different than what I got the first time? I love you guys so much.
I don't know.
I love you guys so much. How could it be different? You're the same people. Do you understand? If I take a group of 2, take your average, a group of 2, take your average, and then average those averages, it's going to be the same as if I took everybody by themselves. Okay, maybe. So the average stays the same throughout the whole thing. So what changes is the standard deviation. So here's what this central limit theorem says. Chicken, lettuce, tomato. Central limit theorem. Central limit theorem. And the name kind of makes sense because as I get bigger and bigger samples, isn't the data that I'm plotting trending towards the middle? Central limit theorem. So 1, the mean stays the same. You're going to love this. No, watch. Stay with me. What was this a picture of? How did I make this picture? By taking one person, individuals. Both of these are by taking groups and plotting their averages. Kick ass. This is a plot of x values. These two are plots of x bar values. Aw, Jeff, what the hell? All right, so the mean of the means. Oh, man. Little subscripts are just identifiers. They are specific types of that variable. So this is the mean of the sample means stays the same. But the standard deviation of the sample means becomes smaller. And tell me, between these two pictures, which one has a smaller standard deviation? This one. More of it's at their mean, more of it's close to the mean, so that should be a smaller spread. So it depends on the sample size. So this new standard deviation for a group of size whatever is equal to what it used to be for individuals divided by the square root of the sample size. So as my sample gets bigger, my standard deviation gets smaller, which is exactly what kind of makes sense. It's exactly what happens if you actually do this. So I wanted to try to give you, so that's the theory of everything. My attempt on this piece of paper here with the, where'd you go? Here we go. This guy. This is my attempt at giving you, what did I just do? Okay. Giving you a, holy shit, that happened. Oh, okay. Oh, man. Honey, I blew up the example. All right. This is my attempt at giving you a concrete example that you can actually kind of see. So let's see if you guys get this. It's not perfect, but it's the best one I can come up with that you can actually kind of get a feel for. So I put 4 numbers in a hat. If I plotted it, would it come out uniform? Because is there any more likelihood of getting any number than another one? If I pick one out of the hat, no. Shouldn't be. Assuming all things are equal, right? So that's what the picture looks like. Does that look normal? No. Hell no. What would it, to be normal, it should be low, high, low. You with me? All right. So that's what I get if I pick one number out at a time. This is the distribution of probabilities I would expect. 25% chance of any one of them. Now, instead of taking one at a time, I'm going to take one, drop it back in, and take another one. So I'm going to take 2 at a time. I'm going to take samples of size 2. So everybody semi with me. Now, do you understand? If I said samples of size 3, this thing would blow way the hell up. So samples of size 30 would not fit on, I'd have to give everybody this much paper. Did you guys follow what I'm saying? Not at all? I can list all the samples of size 2, I did. Can you start to imagine what it would take to list all the samples of size 3 if I wanted to do 3 instead? 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 1, 4, 1, 2, 1, 1, 2, 2. Holy shit, no thank you, right? Okay. So this is not perfect, but it's the best specific concrete example that we can all kind of hold on to. Is everybody cool with what's happening? What happened here? I picked out a 2, dropped it back in, then I picked that same 2 again, right? You guys with me? All right. And then what are these?
Averages. Yeah.
So there's the sample I took, and there's its average. So then I would plot this. There's the sample I took and its average. So what's going to be the highest bar? What's the most common average? 2.5, right? So what I did then was down here, you can see the new table for the means. Sure enough, the highest bar is 2.5. Does that picture look more normal? Yes, I like it. And if you take all the means and do 1 bar stats on them, you do get this standard deviation. Now stay with me. What was the standard deviation of just the 4 numbers in a hat if I took one at a time? I did it up here.
1.118.
So theoretically, the standard deviation of samples of size 2, how spread out the means are from their mean, should be 1.118 divided by the square root of 2, because my sample size is 2. And sure enough, if you do 1.118 divided by the square root of 2, you freaking get what we got for these. If I had more time, I'd make you do all the work, but I don't. So there it is. Okay, so maybe. So this is what happens. The picture, this is what I didn't write down, but central limit theorem talks specifically about the mean stays the same, standard deviation changes, but as n grows, the picture becomes more normal. But what do I really, really want to know? More normal. When is it normal enough? Remember that? Because then if I know it's normal enough, what can I use? That has all the answers on it. Z-score chart. Kick ass. So here's the thing. We ran, well not we, I wasn't there. It was a long time ago. Back in the day when the computer took the whole room, they ran simulations over and over, and they noticed that if it's greater than 30, my sample size is greater than 30, the resulting picture of the means was normal enough. No matter what the shit at the beginning. Now look at this one. Isn't this already looking normal? And you only took samples of size 2, right? But did it start off looking gross? It started off looking beautiful, symmetric. So the 30 number is just for any, no matter how ugly the distribution is, then 30 makes it become normal enough. If my distribution started off nice already, I don't need as big of a sample. Now, what if my distribution starts off as normal? Then I don't give a shit what the sample size is. It's normal. So when do I need to know the sample size is bigger than 30 if the problem doesn't tell me it's normal to start with? What saves my ass then is the sample size. Okay. Now, I just spewed a lot of concept at you, right? The actual thing that changes in a problem is unbelievably minor. So let's try a problem out. Yeah, let's do one on the back together since I love this one. So here's something about bone densities for women. This is a major concern especially for women as they grow older. Is your bone density kind of depletes. But if you read through this, part A is old news. Part A is chapter 6. When does chapter 7 come into play? You ready? This is going to sound like a note. This is a note you should take. The central limit theorem comes into play when I take a sample and I ask a question about the sample mean. Because that standard deviation would change, and it relates to the picture of sample means. So look at 1A. We did a problem like 1A before today. So it definitely can't rely on anything we did today. Do you see how 1A is one just like we did before? What did I tell you about the distribution to start with? We know the mean, we know the standard deviation, and we know that it is normal enough, right? Approximately normal. So 1A, old news. Nothing new. Draw the picture. What's going to be in the middle? What's in the middle? What's in the middle? 2.9, that's the mean. I want to know more than 3. Looks like 2.93. More than 3. So then what do so that's the picture that captures the question. Then I want to do what?
3 times the standard deviation divided by.
Make 3 into a z-score. So 3 minus the mean, right? Divided by the standard. So you guys know 1A is old stuff, right? Make 3 into a z-score. Three minus 2.9 divided by 0.31. It's like 0.32. Is it? 0.32?
Yes.
Dude, all right. Earning my keep. Got to show you I know some shit. And then you look that up, that's not going to be the answer because you want greater than, right? But still, right? So 1A is your classic traditional. I didn't take a sample. I selected one woman. I didn't take a sample of women. So if I look up 0.32, what do you guys get? 6259? 55? So then this will be 0.3745. All right, so that's old news. We did that a ton already. What's different in part? Is everybody cool with that first part? That's the same stuff we were doing earlier. How did I tell it was the same stuff? I took one woman. What's different in part B? Two things. Taking a sample of 22 women. So before today, we couldn't do this worse shit. And I'm asking a question about the sample mean. So the sigma symbol, sigma equal 0.31. That's the spread for what? That's the spread for individual women. How far away are individual women away from their mean? Part B, that's not going to help me worth shit. I need to know how spread out the means are. So I can't use this guy. This is the one for individuals. I need the one that works for groups of 22. So I got to take this guy divided by square root of 22. So that's really what I'm doing when I do that step, is I'm creating a standard deviation for groups of size 22, not just individual one. So very first thing I do, change the standard deviation. What do you guys get for that?
0.066.
Yeah, 0.66. I like it. And so that's the only new thing. I do all the same work I did, except instead of putting 0.31 down there, I'm going to put 0.066. Z-score formula doesn't change. R data minus the mean divided by the spread. You just better use the right spread. That's the right spread for a group of 22. Z-score formula didn't change. I don't know if you guys realize what's happening. So I'm going to do all the same work. The only thing that